Welcome to our Azure Incident Retrospective. I'm David Steele.
I'm Sami Kuba. We work in the Azure Communications team.
In addition to providing a written post-incident review after major outages, we also now host these retrospective conversations.
You're about to watch a recording of a live stream where we invited impacted customers through Azure Service Health to join our panel of experts in a live Q&A.
We had a conversation about reliability as a shared responsibility, so this includes our learnings at Microsoft, as well as guidance for customers and partners to be more resilient.
We hope you enjoy the conversation that follows.
So on June 28th, we had a software load balancer issue, but it happened to be timed around a completely unrelated issue with one of our WAN routers in London, which hindered the investigation into both. So to kick us off, I want to ask Dave Maltz, who runs our networking team, to help us understand these two separate issues that just happened to impact customers around the same time. Can you talk us through it?
Absolutely. I'd like to get started by apologizing to our customers who have placed their trust in us. We know that you depend on high quality network connectivity, and our aspirations are to deliver that. And in this incident, we didn't live up to that. And I understand that it impacts your customers and the things that they depend on in the real world out there. This was a real challenge to us in that Azure's of sufficient size that we had two independent, unrelated things going wrong at the same time. And that led to us taking longer to figure out what was going on. We saw impact across 17 different regions, and that impact was what we call a gray failure. It was intermittent, it impacted only some sets of scenarios and some customers, and so teasing out the true root cause took us far longer than is acceptable to us. And I can tell you about some of the improvements we've made so we get better and faster at this. I'll actually talk about that WAN outage first, because that's the easiest to explain and the easiest to understand. Microsoft operates its own global wide area network, because by doing so, we have complete control over the quality that's delivered to our customers' traffic as it goes across that wide area network. We're able to offer very high quality, very fast response, and lower latency than it's available from traditional internet service providers. It is a global network. We own and operate all of it and all the fiber connected to it. That the network is made up of transoceanic cables, fiber connecting to different cities, and what we call WAN routers. These are very large devices, typically having anywhere from 140 to 250 or so ports on them. Those are basically places where the fiber is being plugged into these routers. You can think of them as the hubs of the nervous system that distributes data across the Azure network. It turns out the true root cause here was that one router in London had 1 out of 140 ports that was experiencing intermittent packet loss. The actual impact meant that 0.4% of the packets going through that router were being dropped and in an irregular pattern. The reason for this was actually due to a hardware issue on that one port, and it was the kind of issue that there was no outward indication of a problem. The router's own software that it uses to monitor its health didn't detect any problem, and due to the nature of that intermittent loss, it actually slipped under the radar of many of the active probing systems we use to externally assess whether each of our routers are being healthy or not. We expect these kind of hardware failures to occur, and so we've built these methods such as active probing and triangulation systems to look for the reports of problems and figure out where those are most likely to be coming from. We have tons of redundancy in our network, so if we can identify a device like this that's sick, all we have to do is turn it off, and the network will almost instantly reconverge and begin carrying traffic correctly or not. The needle in the haystack problem we have is how to figure out which router is responsible. During this date on June, we were seeing issues across 17 different regions in our network. Microsoft consists of over 63 different regions right now, and when we see that kind of widespread issue, it tends not to be due to these sort of wide area network devices. They tend to localize more to problems in 1 or 2 or 3 regions that are actually being connected by those wide area networks. So when we began receiving reports from a wide number of regions, the WAN network isn't where we started to look. It was only as we began to tease out that there were actually 2 issues going on, this wide area network issue, as well as the software load balancing issue. They were able to keep both sets of teams across Azure networking properly investigating. Once we had the insight that we had 2 different things going on, at that point, we're able to look for even more subtle signals of packet loss. And through those, triangulate down into the wide area network and then into this one we call point of presence in London, and then ultimately that one router. That one router is causing, as I say, this intermittent low-level packet loss to essentially 4 regions in Europe. our UK regions, and then our East and North regions. Now, while 0.4% packet loss sounds like a small number, it is certainly enough to cause impact to customers. It can result in slower transmission of data. It can result in some requests being failed. And the way it worked out is it happened to impact a lot of our express route circuits. Those are customers who have paid for a dedicated connection from their on-premise facilities into the Microsoft network. And of course, since their business, both on-prem and in the cloud, often depends on the health of those express route circuits, any loss of traffic there can be impacting to their business. Now, as soon as, again, we figured out which router was causing the issue, we simply turned that router off, and traffic began flowing normally again through our wired network, and all services there returned to healthy. Now, what was going on at the same time that made it harder to triangulate? Well, we had also are continuously in the process of releasing new code changes to the Azure network. We're always trying to fix the problems that we've already detected through what we call repair items, as well as make new capabilities available to our customer. Our software load balancing team is responsible for creating what we call these virtual load balancers. In the internet architecture, customers want to send client requests to a single IP address that they think of as being analogous to the service as a whole. But yet there's no one server that can possibly handle the volume of requests that make up most web services. As a result, people put these software load balancers and configure them to go in front of the worker servers, the many servers that actually do the work for their web service. The job of the load balancer is to take incoming requests to that one virtual IP address and spread them out across all of the healthy workers that sit behind this. In order to do that, we have servers that we call multiplexers. Those are the servers that actually announce reachability to the virtual IP address and have essentially lists of what servers are healthy behind them. We're always making changes, as I said, to try and make this more efficient. And in this case, we were rolling out a code change that would result in these multiplexers being more efficient in how they distributed work across the various DIPs, we call them, the workers that sit behind that virtual IP address. Now, all of the changes that we make to software going out to Azure first goes through an extensive set of tests. We test them individually. We test them as part of what we call stage clusters, where we bring together our entire services but run them in a completely isolated environment. Once a release candidate proves its worth there and that it's working correctly, it's then brought to what we call a canary cluster, where it exposes the full set of workloads that we have running on Azure. Only after it is proven healthy in that canary cluster do we then begin taking it to our production regions. First, what we call the pilot region, and then gradually in larger and larger rings involving more and more production clusters. That's how we gradually build confidence that this software change is going to work correctly. The details of the software change, an issue here, was in how each multiplexer computes the order of healthy workers that it's going to forward traffic to. There is a very subtle change made to the sorting function that's used. And what that resulted in is that as the code rolled out, the multiplexer servers were computing that list of workers in different orders. If they had the new code, they computed the list in one order. If they were still using the older version of the code, they computed the list of healthy workers in a different order. That's very important because there's a lot of stateful communication that happens in the network. And essentially what that would mean is that if a request was forwarded by our network coming in from the internet to one multiplexer that was using the old version of code, it might be sent to one healthy worker for further processing. If that same packet, though, that same request, had been delivered to another one of the healthy multiplexers running the newer version of the code, that multiplexer might decide to send it to a different healthy worker. But because if the first packet in a communication went to one healthy worker, the second packet in a communication went to a different healthy worker, that second healthy worker wouldn't know what to do because it had incomplete information. And that would result in things like a TCP reset signal or potentially a timeout happening to the client who made that request. Basically, what that meant is that while we're in the process of rolling out this change, there was a window of vulnerability where some requests would experience this delay or fail. It made it even harder for us to find it because it turns out that this issue only impacted VIPs that had more than 15 healthy workers behind them. In a bunch of the testing that we didn't monitor closely enough across the transitions as the code rolled out to be able to accurately detect all of these things. That's how that bug essentially escaped from our release qualification process and started rolling out across our fleet. It also turns out that this only impacted two very specific scenarios that use this software load balancer. One primarily is used by our Azure firewalls. It's a particular type of encapsulation that goes to our firewalls, but it meant that customers using Azure firewalls that had scaled out to have more than 15 firewalls working behind them could experience this issue for long-lived connections flowing through those firewalls. That also overlaps a lot with a set of our customers who use ExpressRoute. Remember back when I said that wide area network issue particularly impacted our ExpressRoute customers? Again, that's why it took us too long in order to figure out and triangulate what the issue was, because we knew we had something impacting ExpressRoute customers, but there were two separate different causes that were causing that impact, and we had to tease those apart before we could get to true root cause. The end result of this was that as we began, the second scenario that impacted on our software load balancing was something that impacted what we call service tunneling, particularly people who were putting storage accounts behind a private access method so that their storage virtual IP addresses would only be reachable from their private virtual networks. The end result of this is that as we began to see that the wide area network, there were two things going on. The wide area network issue had been resolved. We also then began to realize there's something else going on impacting those two specific scenarios, essentially our firewalls and our service tunnel endpoints. We began to dig in, understand that this actually did correlate to a rollout of our changing code. And then as we looked back, we did see that in the earlier regions, there was a very faint signal of impact. And we began to identify that it was impacting only customers that had these larger pools of healthy workers behind a virtual IP address. And once we had that, we were then able to begin to mitigate that issue. We first began by doing mitigations to directly restore the health of the VIPs. This was doing what we call reprogramming. We basically re-instructed all of those muxes how to properly use the same list of dips to forward packets. And we then began a rollback of our code as well to a last known good. Combination of those things got us to full mitigation. I do also want to acknowledge that it took us a few days to get the software load balancer issue completely resolved. Some of the things we've done to improve on this, we've improved our monitoring of our network devices. That's helping us triangulate even these low packet loss rates, regardless of what network device it hits. We've put a lot more checks and stress tests into our software load balancing release qualification process. We've also added additional telemetry logging and monitoring to make it easier for us to detect issues, even those that are affecting just small numbers of our customers. Again, thank you for hearing us out and staying with us and maintaining your trust in us as we work through these issues. I'm happy to take questions.
Great. Well, maybe Dave, I can maybe jump in with the first question, and then I think there's some that are coming in from the chat. But I was just kind of curious, given this ended up rolling, some of these updates rolled out to be multi-region, and I saw that someone asked in the chat, maybe could you go into a little bit more depth in terms of how our safe deployment process works, and then in particular for some of these cases where it's sort of 0.4% loss or gray failures that we often call, like, what are things we're doing to improve our monitoring to kind of catch those kind of very intermittent type failures where it's not hard down and easy to detect, but especially with the first region where there's maybe lower traffic, how do we detect those? Maybe share a little bit of the thoughts there.
Okay, sure. I'll start by talking a little bit more about our safe deployment practice. That's the name for this process of gradually rolling out release candidates to more and more regions as we gain confidence in them. We essentially have what we call that bill of health or bill of quality. There's a series of tests and essentially runtime that we expect to get on the code before we'll advance it to begin rolling out through the next region or the next set of regions in the next safe deployment phase. We found this to be quite effective at finding and detecting issues before they go broad across production. In this case, as I said, it did manage to escape until it had made it across 17 regions. That again is why when we were trying to correlate to understand what was going on, made it harder to find that WAN issue because we did see impact across a larger number of regions. Now, things that we're doing to improve the quality of our health gates, to make that bill of quality, that bill of health even more accurate, we're increasing the amount of stress tests that we put on these release candidates. We are making sure that we have what we call runners, basically synthetic tests that are continuously exercising the kinds of workloads that we see coming from our production customers in the cloud on every stage of our network rollout, so that we're using these in our stage, we're using these in Canary, we're using these in pilot. So even when there isn't real customers providing workload, we are providing workload that's exercising our software in the same way that you, our customers, will eventually be exercising it as that release candidate starts to get out into the production regions. So that's how we're making sure that release candidates are fully qualified, and we're not going to see even these edge conditions, if you'll call them that, leak out and cause problems into our production regions.
Super. Dave, I do have a question here. This predominantly impacted big enterprise customers, or customers, as you said, that had more than 15 dynamic IPs or DIPs. We were mitigating them one at a time. Did that inhibit or hinder us when we understood what the issue was and we started putting a broad mitigation in place?
No. So in this case, we had essentially the Azure networking team and its 2,000 members fully at our response availability during this kind of serious issues. So we had multiple teams actually working over this 72-hour period to examine all the possible avenues. We had folks working on work streams, again, at our physical network and our express route code bases, working with the fiber providers and our interconnections to the enterprises, the people who deliver the last mile connections from our data centers to the enterprise data centers, because we knew, again, that this was impacting some of our largest customers, and particularly those with ExpressRoute. So we were working all avenues simultaneously, and when we began understanding what the root causes was, we were able to fork off other work streams to have teams go and look for these immediate mitigations, while we had another work stream beginning the rollback process to roll back that code, as well as another team working to actually put the fix in. Super.
We have another question from some customers about what are the possible resilience options that our customers can take to prevent impact from such a large outage?
That's a great question. So Azure is the cloud. We expect things to fail. Our goal is to build resiliency into our systems and to also create mechanisms that our customers can use to make sure that their services are going to be resilient. Some of the ideas around here is essentially spatial distribution. Bad things can happen in one place, but bad things generally don't happen in multiple places simultaneously. Whether it's geopolitics, whether it's an environmental disaster, power outages, the world is a large place and Azure is present all across that. For those regions, we often geographic diversity, hosting services in more than one region that are spatially separated, is a way of ensuring that no matter what happens to any part of the world, your services will remain up and running. As we do our safe deployment rollouts, we also have this notion of region pairs. We don't roll out our code in multiple regions at the same time if those are part of region pairs. So again, customers can be sure that any change we're making is going to, even if there was an impact, hit only one of their regions at a time. Similarly, inside of our regions, many of them offer availability zones. We ensure that we only roll our code out to one availability zone in a region at a time. We also encourage our customers to work with us to really look in detail about how their ExpressRoute connections, that fiber or the T1, however their local circuit goes from their on-prem facilities to the Azure facilities, where those local circuits will terminate on what we call Microsoft Enterprise Edge devices, MSEEs. We want to make sure that those are physically located in different buildings. So again, no matter what happens, whether it's connectivity to that building, power to that building, or even a construction error breaking fiber going into the building, that their ExpressRoute circuits have spatial diversity and will remain up and running. On top of that, we have other resiliency mechanisms such as Azure Traffic Manager, Azure Front Door, global VIPs, that provide other ways of making sure that no matter where the traffic to your service is coming from and where it's going to, we can distribute that out across your entire footprint and across the world.
Thank you for watching this Azure Incident Retrospective.
At the scale of which our cloud operates at, incidents are inevitable.
Just as Microsoft is always learning and improving, we hope our customers and partners can learn from these too, and provide a lot of reliability guidance through the Azure well-architected framework.
To ensure that you get post-incident reviews after an outage and invites to join these live stream Q&A sessions, please ensure that you have Azure Service Health Alerts set up.
We really focused on being as transparent as possible and showing up and being accountable after these major incidents.
Whether it's an outage, a security, or a privacy event, Microsoft is investing heavily in these events to ensure that we earn, maintain, and at times rebuild your trust. Thanks for joining us.